Hello there and welcome to another part of module 3. In this one we'll be discussing algorithms for addition, multiplication, and we have discussed floating point earlier in the previous lectures, so we'll be focusing on these two algorithms mainly. The addition and subtraction algorithm there are three different ways. Either we have signed magnitude, we have 1's complement, or we have 2's complement. 2's complement is most widely used for subtraction. An algorithm is basically a finite number of defined steps for any problem, and a flowchart is a suitable method for presenting the algorithm in terms of the flow of the instruction. Whenever we are doing addition and subtraction with signed magnitude data, so there are 8 different conditions. We have A and B. They're either being added or they're being subtracted, and in the first case we have A and B both positive, then we have A positive but B negative, we have A negative B positive, then we have A negative B negative. Same way we have for subtraction, both positive, B is negative, A is negative, and both are negative. So this, you don't need to learn the table mostly. This is basically based on logic. So if both are positive, then you are simply adding both of them and the sign will be positive. When B is negative, okay, so there are 3 different cases. If A is smaller, if A is greater than B, then it is simple subtraction of A minus B. Sign will remain positive because A is greater. When A is smaller than B, then you have to subtract B minus A and the sign will change because you'll go towards the negative. Finally, when they both are equal, again the sign will be positive, A minus B. Doesn't make a difference over here. When A is negative and B is positive, so again we have 3 cases. If A is bigger than B, then the sign will be negative and it is subtraction, A minus B. Finally, when A is smaller than B, it will be positive sign, B minus A, because this is the this is the same as B minus A or minus A plus B. So when they both are the same, positive sign and subtraction. If they both are negative, this means it is minus A minus B if you simplify it. So that means the sign will be negative and it is the summation of both the values, so A plus B. If both are same signs but the subtraction is taking place, we have 3 cases again, and this is also same as A minus B. So we have A minus B if A is bigger and the sign will be positive. If A is smaller than B, then B is going to be A is going to be subtracted from B and the sign will become negative, and so on. So these are basic math calculations. You don't need to learn the table. You can derive them on the spot just by looking at the equation and simplifying the version and saying that if A is smaller, if A is bigger, and if they both are equal. Here we have the algorithm where we say that the signs of A and B, if they are identical, we are doing addition, and if they are different, if we have addition, then we'll be considering the word that is out of the brackets, and for subtraction the algorithm is in the brackets. So when the signs of A and B are same, then we add the 2 magnitudes and put the sign of A in the result. When the signs of A and B are different, then we compare the magnitudes and we subtract the smaller one from the bigger one, or if this is smaller, then this will be subtracted from this, and then smaller from the larger one, and finally we choose the sign of the result to be the same as A if A is big, and it will be the complement of A if A is small. So if A is positive and A is a bigger number than B, then the sign will be positive, but if A is smaller than B, and then the complement of positive will be the negative sign, so we'll use the negative sign. If the 2 magnitudes are equal, we subtract B from A and the sign will become positive. Again, for subtraction, the only difference will be that if A and B are different, then we add the 2 magnitudes and get the sign of A. If A and B are same, then we compare the magnitudes, subtract smaller from larger. We just reverse the steps. So the step for identical is the one for identical in subtraction, and the different one is interchanged. They both are interchanged in addition and subtraction. This is the hardware implementation where we have the data of B stored in register B, we have register A, there is the complementer, we have a parallel adder, this is for the carry, and accordingly based on the algorithm we can use the hardware implementation to solve addition and subtraction problems. The flowchart on the other hand is here. For an add operation, we have augend in A, the addend in B. Once we do their XORing, we found out if it's 0, that means they both are equal and they'll be added, and if it is 1, then that is subtraction because they are not equal, So it goes here, and then we do a plus b's complement and so on. We set the carry to the AVF, and that leads to the end, and it results in the, we get the result. On the other hand, same for subtraction. If the XORing is the, if XORing of A and B is 1, that means they are not equal, hence just add A and B. And when it is 0, we have A and B as equal, so they are subtracted. Whenever the cases are reversed in the addition and subtraction, as we saw earlier, if they are not identical, we will add them, and in the case of addition, if they are not identical, we'll be subtracting them. Okay, so that's why these are interchanged. And then we have 0, a equals to b1. Okay, a is equals to b, so we do the complement addition, 2's complement addition. AVF is set to 0, and then we compare the e bit, that is the carry. If it's 1, that means a is bigger than b. So if a is 0, then we set a 0. If a is not 0, this will be the final effect of the output. And similarly we have it here. So throughout the flowchart, we are setting the sign, we are adding and subtracting, comparing them, seeing what the values are of a and b, and on comparison we decide whether we need to do 2's complement or we need to simply add them. The multiplication algorithm has the hardware implementation for signed data as follows. There is a sequence counter, we have a Q register, and its rightmost bit is the QN bit. We have A register and B register. This will store the values that will be multiplied. The complementary and parallel adder is there. We have E, which is for the carry bit, that is initially set to 0. This is the flowchart. So we have the multiplicand in B and the multiplier in Q. The first step will be the XORing of B and Q, and it will be stored in AS. The XORing of Q and B again is stored in QS, and A is set to 0 initially. The enable is also set to 0. Sequence counter is made n minus 1. So we check for Qn, the Qn that was stored. We'll compare and see if Qn is 1, then we'll be adding A and B. We'll add the multiplicand to A, and then we'll do shift E, A and Q. We'll shift all of them towards the right, and sequence counter minus 1. Okay, so this will repeat again and again. We'll compare Qn value. So Qn will be the one that will define the flow of the multiplication operation. If Qn is 0, we'll just shift each 3 of these to the right, and sequence counter minus 1. And once sequence counter becomes 0, this is the end, and the product is the final. The final answer will be AQ. So the values of A and Q written together will give us the final product. Here is an example. We have multiplicand B, we have E set to 0, we have A 0, our Q is given here, and our sequence counter is 101. We get the sequence counter, this is the binary for 5, and it is the same as the number of bits of the multiplicand and multiplier. We have 5 bits here, that means we will use the binary value 5 for the sequence counter. The first step is to see what the value of Qn is. Qn is always the lastmost bit, which is 1 in this case, hence we'll be adding B to A. By adding B to A, we get this following output. There is no carry, and then we shift to right. We have to shift E, A and Q, so all the values will be shifted and the last bit of Q will be discarded, and a 0 will be pushed in, and E remains 0. So this will be the output after pushing it. Sequence counter minus 1, and then again you are going to look at Qn, which is 1. Okay, so again we're going to add B to the value of A. We get this output. There is a carry bit here, and then we're going to shift right, so 0 gets pushed to the E bit and the 1 goes towards A, and so on. The last bit is discarded, and sequence counter minus 1. We can see that Qn is now equal to 0. In this case, the Qn becomes 0, hence we will only shift right the E, A and Q. After shifting right, we see that the 0 is discarded. Again it is 0, so we will shift it right once more, and this will be the output. Sequence counter will be decremented each time. We get to 001. We can see that this is the last step. At this we find Qn equals to 1, so we'll be adding B to A, and this will be our addition. This is a simple binary addition, so 0 plus 1 will give you 1, 1 plus 1 will give you 0, and there will be a carry, and 1 again. So after you do the addition,
you will shift right E, A and Q. So once you do that, the sequence counter becomes 0 0 0, hence the final output will be A Q. So this is the Booth algorithm for multiplication. The hardware for Booth algorithm is used as follows. We have BR register, we have AC register, complementer and parallel adder. The sequence counter is there. QR register has Q power Qn, the Qn bit and the Qn plus 1 bit. The Qn plus 1 bit is used in the algorithm where we may have subtraction, or it is basically used in the signed numbers. We have an example coming up. So if we have 2's complement, that is when the Qn plus 1 is used. So again we have the multiplicand in B and multiplier in Q. You may take QR, B and PR, that is just the register, so the name can be anything. The AC will be set to 0, also the same as A in previous. A is set to 0, Qn plus 1 is also set to 0, sequence counter is set to N. We go to the values, we compare Qn and Qn plus 1, both will be compared together in this case. So if Qn and Qn plus 1 are 0 1, then we'll be adding A and B as we did previously, A plus B, and then we'll be shifting. We'll be doing an arithmetic shift here because this is the algorithm for signed numbers. Okay, so we have to do an arithmetic shift so that we can keep the sign of A, C, Q and R. Okay, so A, C, Q, R, so basically A and Q, and finally sequence counter minus 1. We go to sequence counter, it is not 0, we'll come back again, and in this case, now in this step, if we have Qn and Qn plus 1 as 1 0, then we are gonna do subtraction. This is addition of 2's complement of A and B. We are subtracting A and B, and then again arithmetic shift right and sequence counter minus 1 up until we complete the loop of these steps, which will finally give us the final product. Here is an example. We have BR as 1 0 1 1 1, and hence its 2's complement is going to be 0 1 0 0 1. We can find the 2's complement pretty easily. All you have to do is you have to complement all the values and then you have to add 1 to it. So the complement of all these values become 0 1 0 0 0, and then when you add 1 to it, it becomes 0 1 0 0 1. Fine. This is how you find 2's complement. You are going to write AC as 0 initially. You have QR will be given to you in the question. Qn plus 1 is 0. Sequence counter is set to 5 because we have 5 bits. And then at the first step we are going to see Qn is 1 and n plus 1 is 0. Okay, so 1 0, which is the state for the left side of the flowchart. We saw subtraction, so we're going to subtract both of them, or you can say the addition of 2's complement. Fine, this is the output we get, and then arithmetic shift right. The signed bit is going to be pushed, so we have all the values pushed to once and once to the right, and then we have sequence counter decrement. Now we have Q and Qn plus 1 as 1 and 1. Okay, so 1 and 1 means we have just shifting. We are just going to shift because it's neither of the two cases, so all we'll do is we'll just shift. So no adding, only shifting. Just shift each of them, and then in the next case we have 0 and 1, which leads to addition of BR. So we'll add BR. Remember, you have to add BR, not 2's complement of BR. We'll be adding BR to A. Once we add that, we'll shift arithmetic right. So you'll push the 1 bit, so it'll become 1 1 1, and all of them will shift. Since we have 0 0, again it does not match either of the two conditions. We will be shifting right. Again we shift right, we get 1 0, which is the case for subtraction. In Q, the Qn bit and Qn plus 1 bit, 1 0. So we'll subtract BR, which is the addition of 2's complement. So you just add 2's complement to the number and you'll get this output. And finally, to complete it off, the arithmetic shift right, and this will be the final answer. Since the sequence counter is now 0 0 0, our answer will be A, C, Q and R. So once we write these together, this will be the product for the multiplication of BR with QR. As in the multiplication schemes, Booth algorithm requires the examination of the multiplier bits and the shifting of the partial product. Prior to the shifting, the multiplicand may be added to the partial product, subtracted from the partial product, or left unchanged according to the rules. Multiplicand is subtracted from the partial product upon encountering the first least significant one in a string of ones in the multiplier. We add the multiplicand to the partial product if we have the first 0, provided there is a previous 1. So 0 1 is when we add. At 1 0 we subtract. Okay, and no change when the multiplier bit is identical to the previous multiplier.
Thank you and see you in the next video.